Carbon is one of the most essential elements in the universe. With the atomic number 6 and the symbol C on the periodic table, it plays a central role in chemistry, biology, and materials science. Found in everything from diamonds to DNA, carbon is unique in its ability to form complex and stable bonds, making it the backbone of all organic molecules and a cornerstone of life on Earth. At the atomic level, carbon has 6 protons and, in its most common isotope, 6 neutrons in the nucleus, with 6 electrons orbiting the nucleus. These electrons are arranged in 2 energy levels, 2 in the first shell and 4 in the second. It's the 4 electrons in the outer shell that make carbon especially interesting. With 4 valence electrons, carbon has the ability to form 4 covalent bonds with other atoms. This allows it to create a wide variety of structures, from simple molecules like methane to complex macromolecules such as proteins and nucleic acids. Carbon exists in several different forms known as allotropes, each with unique properties. The most well-known allotropes are diamond, graphite, graphene, and fullerenes. Diamond is an incredibly hard substance in which each carbon atom is bonded to 4 others in a 3-dimensional tetrahedral structure. This arrangement gives diamond its strength and its famous sparkle due to the way it refracts light. In contrast, graphite is soft and slippery. Its carbon atoms are arranged in layers of hexagonal rings, where each carbon is bonded to 3 others, forming planar sheets. These layers are held together by weak van der Waals forces, allowing them to slide over each other easily, which is why graphite is used in pencils and as a lubricant. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, has generated intense interest in the scientific community since its discovery. It combines remarkable electrical conductivity, strength, and flexibility, and holds promise for a wide range of applications from electronics to biomedical devices. Fullerenes, another allotrope, consist of carbon atoms arranged in hollow spheres, tubes, or ellipsoids. Buckminster fullerene, or C60, is shaped like a soccer ball and has potential uses in nanotechnology and drug delivery. Carbon's versatility is not limited to its physical forms. Its chemical behavior is equally impressive. Carbon forms the basis of organic chemistry, which studies compounds containing carbon-hydrogen bonds. Organic compounds include everything from fuels like propane and ethanol to the fundamental molecules of life, such as carbohydrates, lipids, proteins, and nucleic acids. Carbon's ability to form long chains and rings and to bond with other elements such as hydrogen, oxygen, nitrogen, phosphorus, and sulfur allows for the vast diversity of organic compounds. One of the most critical aspects of carbon's role in life is its presence in carbon dioxide, CO2, and its role in the carbon cycle. Carbon dioxide is a greenhouse gas found in Earth's atmosphere. Plants absorb it during photosynthesis, using sunlight to convert carbon dioxide and water into glucose and oxygen. This glucose serves as an energy source for the plant and for the animals that consume it. When organisms respire, carbon is released back into the atmosphere as CO2. Carbon is also stored in fossil fuels, oceans, and soil. The carbon cycle is vital for maintaining the balance of carbon among the biosphere, atmosphere, oceans, and geosphere. Carbon is also a major component of fossil fuels, coal, oil, and natural gas, which are primarily composed of hydrocarbons. These fuels are the result of millions of years of pressure and heat applied to ancient plant and animal remains. When burned, they release energy as well as carbon dioxide. The widespread use of fossil fuels has led to an increase in atmospheric CO2 levels, contributing to global warming and climate change. This environmental impact has sparked a search for cleaner energy sources and more sustainable uses of carbon. In industry, carbon has a wide array of applications. Activated carbon is used in filtration systems to purify air and water due to its high surface area and ability to absorb impurities. Carbon fiber, made by weaving strands of carbon filaments, is extremely strong and lightweight, used in aerospace, sports equipment, and automotive engineering. Carbon black, a fine black powder, is used in making tires and inks. Steel production also relies heavily on carbon, where it is alloyed with iron to improve strength and durability. From a historical perspective, carbon has been known since ancient times, although not by its modern name. Charcoal, a form of impure carbon, was used by early humans for drawing and cooking. The understanding of carbon as an element emerged with the development of modern chemistry in the 18th century. French chemist Antoine Lavoisier was one of the first to recognize carbon as an element, and he conducted experiments that helped clarify its properties and reactions. On a cosmic scale, Carbon is the fourth most abundant element in the universe by mass, following hydrogen, helium, and oxygen. It is formed in stars through a process called stellar nucleosynthesis. When massive stars exhaust their hydrogen fuel, they begin fusing helium into heavier elements, including carbon. When these stars explode as supernovae, they scatter carbon into space, where it becomes part of new stars, planets, and eventually, life. Carbon also plays a critical role in astrobiology, the study of life beyond Earth. Its unparalleled ability to form complex, stable molecules makes it the most likely candidate for the chemistry of extraterrestrial life. Scientists search for carbon-based molecules in meteorites, planetary atmospheres, and distant star systems as possible signs of life or prebiotic chemistry. In modern science, carbon continues to be a source of discovery and innovation. Researchers are developing carbon-based nanomaterials for use in batteries, supercapacitors, sensors, and drug delivery systems. Carbon nanotubes, for example, are cylindrical molecules with extraordinary strength and electrical properties. They may revolutionize electronics, construction, and even space travel. Meanwhile, efforts to capture and store carbon dioxide or convert it into useful products through chemical reactions are part of strategies to combat climate change. In conclusion, carbon is much more than just an element. It is a fundamental building block of matter, a key player in both the natural world and human technology, and a source of endless fascination and utility. From the deepest parts of the Earth to the farthest reaches of space, carbon connects the chemistry of life, the structure of materials, and the dynamics of planetary systems. Its story is not just one of atoms and molecules, but of evolution, innovation, and sustainability.